Today we're going to discuss on the topic refraction and lenses. This is a crucial discussion because you have to have known the facts and information presented in this video in order to understand our entire video series related to optics. Come and enjoy Art D Science, which touches the artistic places of science and makes people informed. Let's inquire about the incident refraction. The velocity, wavelength, and the traveling direction of light differs when it travels from one medium to another. This is called refraction. A light ray comes through one direction. After meeting the common interface which separates the two transparent media, it travels through another direction. This is the incident ray. And this is the refractive ray. We can express this idea in another way. When we drew a perpendicular to the interface at the point of incidence, the angle the particular ray forms with the perpendicular differs when it travels from the first medium to the second. This is the angle of incidence. We identify it using I, and this is the angle of refraction. It's identified by R. Then we define something called refractive index. Is sin I over sin R and is represented by N. Next, there are two principles related to the refraction called Snell's laws. First one is that the incident ray, the refractive ray, and the perpendicular must be on the same plane. Second one, the refractive index is a real number, constant for each particular couple of media. Then I'm gonna discuss about another side of refraction. Refraction is caused by the difference of velocity and wavelength of light in the two media. Hence refractive index is also defined as V1 over V2 and lambda 1 over lambda 2. V and lambda are combined together according to the formula V equals F lambda. Frequency F means the number of oscillations per second. Wavelength lambda means the shortest distance between any related similar points of two consecutive oscillations. That is how far the wave travels within an oscillation. Therefore, F lambda multiplication represents how far the wave travels within a second. That is velocity V. So V equals F lambda. In refraction, frequency of the wave, which we call F, is always constant. So the greater the lambda is, the greater the V. That's why N is equal to both V1 over V2 and lambda 1 over lambda 2. Then let me explain how light bends because of the difference of lambda and V. You know light is also some kind of a wave. It's an electromagnetic wave. Whatever the wave type is, any wave can be modeled by this shape. We can introduce a new model for a wave using these crests. We create lines tracing the crests and they're called wave fronts. The wave always travels through a perpendicular direction to the wave fronts. As shown in these diagrams, cause the wavelength of a particular ray differs from medium to medium, the wave fronts have to take place as this. The gap between two wave fronts differs from medium to medium. Then the light ray must bend, cause it always travels perpendicular to the wave fronts. This is why light refracts. When two media are compared, the medium which owns the greater speed for light is called the rare medium, while the other medium is called the dense medium. When a light ray goes from a dense medium to a rare medium, the wavelength increases. So as we showed before, it bends out of the perpendicular. The greater the angle of incidence is, the greater the angle of reflection. Why? N equals sin I over sin R. Both I and R can't exceed 90 degrees. Between 0 and 90 degrees, the sine function increases along with the angle. So the greater the I, the greater the R should be. Finally, at one stage while increasing, R becomes 90 degrees. At this stage, light ray travels along the interface. This is called critical reflection. Here I should exactly be less than 90 degrees. It's called the critical angle and symbolized by C. It's constant for a particular couple of media. When I is increased a little more than C, the refracted ray returns back to the first medium. This is called total internal reflection. Here I and R are same in size. By today, the optical fibers have become an efficient mode of communication. The theory used in them is this total internal reflection. Also, the mirage, which is a natural optical illusion, is caused by this incident. During any refraction, some part of energy reflects. This is called partial reflection. This is the very reason for forming rainbows. Then we're gonna learn about lenses. Mainly there are two types of lenses: convex lenses and concave lenses. They've been created using or getting related to a couple of similar solid spheres as this. These are called centers of curvature. This is the principal axis. This is optical center. Light gets into the lens through this area. It's called aperture. A lens is a focus. The focus of a convex lens is defined where the rays come parallel to the principal axis convergent to. Of a concave lens, the focus is where the rays come parallel to the principal axis seem to be diverging from. The distance between the focus and the optical center is called the focal length. Focal length of a convex lens is considered as a negative value, while that of a concave lens is considered positive. The plane goes through the focus is called the focal plane. Any parallel beam comes towards the lens converges into or seems to be diverging from a point on the focal plane. That point can be found by inquiring where the ray goes through the optical center and parallel to the beam cross the focal plane, as shown in this diagram. Of a concave lens, the same pattern. There's a standard notation for lenses. The distances measured through the direction of light traveling are considered negative values, and the distances measured in contrary side are considered positive. There are some specific types of rays we can exactly say how they get refracted by a lens. Number 1. A light ray goes through the optical center of the lens, travels straight away without any bent. Number 2. A light ray comes parallel to the principal axis, goes through the focus of a convex lens, and seems to be going away from the focus of a concave lens. Number 3. This is the opposite behavior of the above one. A light ray comes through the focus of a convex lens, and comes to the focus of a concave lens, goes parallel to the principal axis. The reasons for the above behaviors will be explained later in this video. However, using any couple of the above rays, we can verify how images get created by a lens and what their aspects are. Let's see how we can do it. To have a nice and complete understanding about images, please watch our video on what are images. It will tell you what we do really see as images. Okay, this ray goes through the optical center without any bent. This ray comes parallel to the principal axis, and goes through the focus. The place where these two rays cross each other is recognized to take place the image. Didn't you understand this execution very well? Watch the video What Are Images? So we can predict the attributes of this image. What are they? The image is smaller than the object, so we call it minimized. As well, the image is upside down. This is a real image, because it's created adjoining real light rays. In a plane mirror, real light rays don't meet one another, so that image is a virtual image. We can take a real image onto a screen, but a virtual image can't be taken. Then I'm gonna move to another important point in optics. That is lens formula. Let's see how to build it up. Look at this ray diagram. Triangle POO prime and triangle PII prime are equiangular. So PO over OO prime equals PI over II prime. We can change it as this. OO prime over II prime equals PO over PI. Furthermore, triangle PMF and triangle FII prime are equiangular. PM over PF equals II prime over FI. We can change it just like the previous one. PM over II prime equals PF over FI. Since PM and OO prime are equal in size, we can replace this PM with OO prime. So OO prime over II prime equals PF over FI. From both of these equations, we can have PO over PI equals PF over FI. Let's take PO as U, which is the distance from the lens to the object, and PI as V, which is the distance from the lens to the image. PF equals F, which is the focal length. Then FI equals V minus F. I'll substitute with these values in this equation. U over V equals F over V minus F. Then I'll solve it. U times V minus F equals VF. UV minus UF equals VF. Now let's divide the entire equation by UVF. It's 1 over F minus 1 over V equals 1 over U. Finally we can have 1 over V plus 1 over U equals 1 over F. If I use this method for various types of images formed by both convex and concave lenses, I can have different equations. But we should have a common lens formula. For that requirement, we use the standard notation about lenses which we previously discussed about. According to the standard notation about lenses, as V is measured through the direction of light traveling, V is negative. U is measured through the contrary side. So U is positive. Focal length of a convex lens is negative. Then I'll engage those marks in this equation. 1 over negative V plus 1 over U equals 1 over negative F. Multiply the whole equation by negative 1. Then, after all, we can have 1 over V minus 1 over U equals 1 over F. This is the lens formula. You can use this for any convex or concave lens. But you must use the standard notation compulsorily. You can meet the usages of lens formula if you watch the other videos of the optics series. Finally, I try to inquire what mechanism takes place inside the lens to refract a light ray. The specialty of our videos is that we always try to find the reasons and mechanisms for the processes and incidents we present you. Why do you think we do so? This is what the science is. Perhaps you may have heard about prisms. A glass prism can change the direction of a light ray as this. It refracts any light ray twice. As I previously mentioned, when a ray goes from a rare medium to a dense medium, it bends inside the perpendicular. When a ray goes from a dense medium to a rare medium, it bends outside the perpendicular. This is a glass prism put in the air. Glass is dense comparative to air. So this light ray first bends inside the perpendicular, and then bends outside the perpendicular. So the light ray behaves as this. If we put the prism in a dense medium comparative to glass, the ray first bends outside the perpendicular, and then bends inside the perpendicular. So it behaves as this. Also, if we put the prism upside down in the air, the ray behaves just like this. A lens could be considered to be made of an infinite number of different prisms with different angles. So we can consider the refractive plane for any particular ray in a lens as the same as in the related prism. Therefore, inside a lens, a light beam can be recognized to behave having refracted by various prisms. Hence, in the air, a convex lens behaves as a converging lens, while a concave lens behaves as a diverging lens. Cause a concave lens is made of the upside-down prisms as in the above form. But if we've put these lenses in a comparatively dense medium, it would be the opposite. The convex lens would behave as a diverging lens, while the concave lens would behave as a converging lens. Now we have to find the reason for not bending a light ray which goes through the optical center. But before that, we ought to have discussed about another important fact. We talked about how various types of rays are refracted by lenses. Those principles suit only for lenses that are imagined to have no thickness. But every practical lens has a thickness. The smaller the thickness compared to the radius of curvature, the distance between the optical center and the center of curvature, is the more nearly accurate these principles. The refraction made by a lens on a single particular ray could be considered as a refraction made by a prism on it. A prism always has an internal refracted ray as this, apart from the outer rays. The existence of this internal ray is the reason for this problem. Because of this, a lens doesn't even have a certain point as the focus. We can get this proven by this simple practical test. Take a convex lens, a source of light just like a torch, and a piece of white paper. Hold these three components linearly as this, and lighten the torch. Then move the paper away from the lens very slowly. You can observe a light spot on the paper. When the paper is being drifted, it's getting smaller and becomes a point. After that, it starts to get larger gradually. This spot is created by the light rays refracted by the lens. If the focus is merely a certain point, it can't have an area. But this point is visible to us. It says that this point has some amount of area. Hence we can prove that the focus of a lens is not certainly a typical point. The light rays come parallel to the principal axis, get associated at a range of points, spread within a very small area. This is the refraction on a light ray done by a lens. When the ray goes through the optical center, these edges of the prism gets parallel. The prism becomes a block of glass. When a light ray is refracted by a glass block, these two rays are parallel. But there happens a displacement between them. But when the thickness is too smaller, that displacement could be neglected. Of a concave lens also, this is what takes place. So we get to sense that a light ray travels through the optical center of a lens, goes straight away without any bent. But don't forget there's a slight displacement which could be neglected.
Thank you for watching this video. If you gained something from this video, don't miss to like it and share it. Subscribe my YouTube channel for more video like this. Click the bell icon for getting a notification about my channel. See you again.